Okay, 12.3, tangent lines and velocity. So tangent lines are something that you've studied in geometry. It is a line that will touch a curved area or a curved function in just one place. So if you remember, starting in chapter 1, we calculated the average rate of change between 2 points. That was when we were maybe given, just like you're seeing here, if we had a point here, maybe at 2, 3, and then we had another point here, maybe at 3, 5, we would draw a secant line and we would calculate the average rate of change for this function using the rate of change for the secant line. So we're going to do very much the same thing today, but we are still going to find the slope of the secant line through 2 points. As we study these sets of graphs right here, you have what looks to be like maybe a quadratic function, and as we go from graph 1 to graph 2 to 3 to 4, look at what happens to the points on the function. So as you can see, they start out pretty far apart, and then in graph 2, it gets a little closer, and finally in graph 4, it's just 1 point. And what's happening every time is this h value is getting shorter and shorter and shorter until eventually h is 0. So what we're going to do today is we're going to do an instantaneous rate of change, which is we're going to find the slope of this tangent line right here. And the way that we do that is we're going to look at the limit as h, or that horizontal distance, approaches 0. So let's fill in these blanks. As the right point moves closer to the left, the secant line provides a better linear approximation of the curve near that point. The best linear approximation is called the tangent line, and that's the best way for us to see the instant rate of change right there at that point. The slope of this line represents the rate of change in the slope of the curve at that instant, known as the instantaneous rate of change. Okay, so to find the slope of that tangent line, we're going to use the following formula, which looks kind of intimidating, but it's really not that bad at all. So the instantaneous rate of change of this graph, f of x, at a point, x and its y value, f of x, is the slope of the tangent line right there at that point, and it is given by this. We are going to do the limit as h approaches 0, so we're going to be evaluating a limit of f of x plus h minus f of x itself divided by h. So it is still kind of like the slope formula, but we don't have 2 points. We just have that h value. So we're taking x plus an h minus f of x, so we're getting that difference. And then we don't have a difference of x values, we just have h, and again, we're letting h approach 0. So this is going to give us the limit of the function, which will in turn be the slope. So for example 1, find the slope of the line tangent to the graph of y equals x squared at 1, 1. So the graph that we have is a parabola, y equals x squared, and we're going to use particularly this x value of 1. That's the location that we're at, and x is in my formula, so we're going to be using that value. Okay, so the slope is going to be the limit as h approaches 0 of, now it's f of x plus h. Well, my x value is 1, so we're going to plug in 1 plus h. So I want f of 1 plus h minus f of 1, my x value is 1, all over h. So now I'm going to substitute. I'm going to go to my formula, f of x, and wherever I see an x, I'm going to put in a 1 plus h, and I'm going to do the same thing. I'm going to square it because it's y equals x squared, so it'll be 1 plus h squared minus f of 1, which is 1 squared, all over h. So I have f of x plus h all squared, or 1 plus h in this case, minus f of 1 all squared. So again, I just plugged in 1 plus h for x and 1 for x, and I'm subtracting them in the numerator and dividing by h. So if you look at this right now, plugging in 0 for h would be indeterminate because it would give us a 0 in the denominator. So we're going to now evaluate and simplify this function, and that h in the denominator is going to cancel. So I'm going to FOIL the top. That would be 1 plus 2h plus h squared minus 1 all over h. The 1 minus 1 cancels, and I have an h in both terms, so I'm going to factor out an h, and it would be 2 plus h all over h, which cancels. And now that the h is out of the denominator, I can go back and take the limit as h approaches 0 of 2 plus h, and we know now that we can evaluate this limit by replacing h with 0, and my slope of my tangent line is 2, because that would be the value of the limit as h approaches 0 of 2 plus h. Okay, let's try b. So now we want the slope of the line tangent to the graph of y equals x squared plus 4 at negative 2, 8. So negative 2 is my x value that I'm going to use, and my function is x squared plus 4. So we're going to take, actually, let me change this. We're going to have the limit as h approaches 0. The first one is f of x plus h. So I'm going to take negative 2, f of negative 2 plus h minus f of negative 2 all over h. So if you need to pause the video and kind of look at what is going on and kind of study that, absolutely do that. I don't want this to go too fast for you. So now I'm going to substitute this negative 2 plus h in for x squared. If I'm going to evaluate the function at negative 2 plus h, I'm going to substitute. So I will have negative 2 plus h squared and then plus that 4. Don't forget about the 4. And then I'm going to subtract my value, my f of negative 2. So I'm going to plug in negative 2 to my x squared, and then square that and add 4. So there's just my substitution, and again, it's all over h. So if I simplify the top now, I'm going to FOIL, and I get 4 minus 4h plus h squared plus 4, and then minus negative 2 squared is 4, plus 4 is 8, and that's all over h. So now I'm just doing some algebra 2 and simplifying things. And 4 plus 4 is 8, minus 8 all cancels and reduces. So now I'm going to factor out an h from the top. I'm going to take out an h, and I have negative 4 plus h all over h, and the h's cancel, which allows me now to do the limit as h approaches 0 of negative 4 plus h. It's no longer an indeterminate form. I can now evaluate this limit as h approaches 0, and by substituting in 0, and it would just be negative 4. So the limit as h approaches 0 is negative 4. Okay, so in these two problems, I had points that I was evaluating the slope of the tangent line at that point. As we look at this next example, we're going to use the same formula, but we're going to do things a little bit differently. Now I want an equation, so I'm going to have an x value left in my final answer because I want an equation. Whereas in these other ones, find the slope. Find the slope. They were actual numbers. No variables were left. Okay, so we want to know our end game going into the problem. Finding an equation means I'm going to have an x left in my answer. So finding the equation for the slope of the graph y equals 4x. So that is my f of x is 4 over x. And this is going to be at any point, which is another way that you know you need to end up with an equation. So I'm going to still take this formula, find the limit as h approaches 0 of f of x plus h minus f of x all over h. So there's my formula. So as I go to my function, I am going to replace x with x plus h. Ready? So I'm going to take 4 over, not x, but x plus h, and I'm going to subtract the function, which is 4 over x, and that's all over h. So just substituting. Now I'm going to do some algebra and get a common denominator up top. I'm going to simplify this down because this is an indeterminate form. Plugging in 0 right here is going to leave me with no conclusive limit. So I need to simplify this. I'm going to get a common denominator of x times x plus h. So here I need an x. Here I need an x plus h. And let's simplify. It's all going to be over h. So I get 4x minus 4 times x plus h. And we'll simplify again. So that's 4x minus 4x minus 4h all over x times x plus h all over h. 4x minus 4x cancels. And so I'm left with negative 4h over x times x plus h. And I'm dividing by h. So what that really is multiplying by the reciprocal. So I'm going to take negative 4h over x times x plus h, and dividing by h is the same as multiplying by 1 over h. And now those cancel. And I'm left with, now I can do the limit because I have canceled that h in the bottom. Now I still do have one down there, but it's not going to make it indeterminate. The limit as h approaches 0 of negative 4 over x squared plus xh. I do have an h in the denominator, but I can evaluate this limit with direct substitution, and my equation for the slope is negative 4 over x squared. So this is my answer. This is the equation for the slope of this graph at any point. Okay, let's look at the next one. Find an equation. So once again, I'm looking for an x value for the slope of the graph at any point. So I am going to do the same thing. I'm going to take the limit as h approaches 0 of f of x plus h. So I am substituting in x plus h to every place that has an x. Ready? So we're going to do x plus h squared minus 4 times x plus h plus 2. There's my f of x plus h, and I'm going to subtract that function, x squared minus 4x plus 2, and it's all divided by h. And now we do some algebra 2. So we FOIL x squared plus 2xh plus h squared minus 4x minus 4h plus 2 minus x squared minus 4x, plus 4x, sorry, it's minus a negative, and minus 2 all over h. And now we're going to cancel some things. I have a positive x squared and a negative x squared. I have a positive 4x and a negative 4x. I have a positive 2 and a negative 2. So everything I'm left with has an h in it, and they're not like terms. So as I rewrite this, I'm going to factor out an h, and I will have 2x plus h minus 4 all over h, which cancels. So now I can look at the limit as h approaches 0 of 2x minus 4 plus h, and I just rearrange those, you don't have to. But here I can do my evaluating the limit by direct substitution. I plug in 0, and I get 2x minus 4. So that is the equation for the slope of the graph at any point. Okay? All right. Now we're going to move on to instantaneous velocity. So this is going to give us speed. Velocity is speed with, again, the added dimension of direction. So we can calculate average velocity the same way we did average speed in Chapter 1. Not sure if you remember that, but here's what we did. You would take two different points in time, you would find their values, and then you would take the average of that. So average velocity states this: if you have a position given as a function of time for any 2 points A and B, here's how you find average velocity. Here's the notation, V with a little sub AVG. It's going to be your change in distance over change in time. And you can totally think of this as the change in your Y over the change in your X, but you will have to find these. Okay, so let's look at this first example. The distance in miles that a runner competing in the Boston Marathon has traveled after a certain time t in hours can be found by this equation. F of t equals negative 1.3 t squared plus 12t. What was the runner's average velocity between the second and third hour of the race? So we want average velocity over time. So we want it between the second hour of the race and the third hour. So I'm going to find time equaling 2 and time equaling 3. So f of 2 will be negative 1.3 t squared plus 12t. And that is going to give me 18.8. And then at time 3, f of 3 is going to equal negative 1.3 t. Oh my goodness, I didn't even plug these in. I'm just talking and not even thinking about what I was saying. Sorry, back up here, I plug in a 2 squared and a 2. And when you calculate those, you get 18.8. When I use 3, I take negative 1.3 times 3 squared plus 12 times 3, and that's going to give me 24.3. So make sure that when you calculate those, you can get those values. So now, using my formula for average velocity over the second and third hour of this race, I'm going to take my f of 3 minus my f of 2, my time on the third hour, minus my time on the second hour, and subtract 3 minus 2, the difference in time, which would be 1 hour. So I get f of 3 is the 24.3, and that's minus 18.8 over 1. So my average velocity is going to be 5.5 miles per hour. And that's average velocity. Okay, now average velocity is going to turn into instantaneous velocity. So in example 3, we found velocity by calculating the slope of the secant line that would connect the 2 points at time 2 and 3. The velocity that was calculated is the average velocity traveled over a period of time. To find actual velocity at a specific point in time, we are going to find the instantaneous velocity. Okay, this is achieved by finding the instantaneous rate of change of the graph of f of t at t. So what's exciting about this is we've already done this. This is just like example 1 and 2, only the t's, if you take a look at this function, where the x's were, they're now t's. So it is the exact same thing that we did. All right, only now they're going to present it to us in more of an application type sense. So instantaneous velocity is this. It is a function of time. An object is traveling over a period of time. The instantaneous velocity is saying that at one point in time we can find its speed, and it is, the limit is h approaches 0 of f of t plus h minus f of t, all divided by h. So example 4 says, a baseball is dropped from the top of a building 2,000 feet above the ground. The height of the baseball in feet after t seconds is given by this equation, negative 16t squared plus 2,000. Find the instantaneous velocity at 5 seconds. So I am actually going to do t equaling 5 seconds at the end. You can plug it in right now if you want, but a lot of times we have to find the instantaneous velocity equations. So that's what I'm going to do first, and I'm going to plug in 5 at the end. But you can try plugging in 5 for t right now if you'd like. That's totally up to you. You will get the same answer. Okay, so I'm going to find the instantaneous velocity equation. So the limit as h approaches 0 of f of t plus h. Actually, let's just go right to writing that in. If I'm going to replace t with t plus h, I'll have negative 16 times t plus h all squared plus 2,000. And I'm going to subtract the function itself, negative 16t squared plus 2,000. And that gets divided by h. So now we have some algebra to do. Okay, negative 16t plus h, I'm going to do the negative 16, I'm going to square t plus h, so t squared plus 2th plus h squared plus 2,000. And then the function is going to be plus 16t squared minus 2,000 all over h. Okay, so then I'm going to simplify this some more and carry through the distribute the negative 16. So negative 16t squared minus 32th minus 16h squared plus 2,000 plus 16t squared minus 2,000 all over h. And as I simplify, I have a positive 16t squared and a negative 16t squared, a positive 2,000 and a negative 2,000. Everything that I have left has an h in it, so I'm going to factor the h out of the top, and I'm left with negative 32t minus 16h over h, and those cancel. So now that I've lost that h in the denominator, I can look at the limit as h approaches 0 of negative 32t minus 16h. And I can do this, evaluate this limit by plugging in 0, and I get negative 32t. That is my instantaneous velocity equation. But they wanted at 5 seconds. So I'm going to do negative 32 times 5, which is negative 160 feet per second. Now you will get the exact same thing if back at the beginning you plugged in 5 for t. Your numbers may be a little bit bigger along the way, but regardless, it does not matter, whatever you'd rather do. And by the way, it's a negative 160 because the baseball is falling, so that's a way to indicate the direction. Since we are talking about velocity, you'll get a positive or a negative to indicate direction. Okay, and the last one. The distance a particle moves along a path is given by s of t equaling negative 3t squared plus 18t minus 1, where t is given in seconds and the distance of the particle from its starting point is given in centimeters. So find the equation for the instantaneous velocity of the particle at any given point in time. So I need an equation, not one value. This other one wanted instantaneous velocity at seconds, so I needed a number. But now I want an equation to be able to evaluate at any point in time. So we're going to use that formula, the limit as h approaches 0 of, I'm going to plug in t plus h, so negative 3 times t plus h squared minus 18 times t plus h minus 1, and then I'm going to subtract the function itself, negative 3t squared plus 18t minus 1 all over h. Okay, and now I'm going to do some algebra. So negative 3 times foiling the t plus h is t squared plus 2th plus h squared minus 18t minus 18h minus 1. And I'll tell you what, I'm running out of room, so I have the luxury of just being able to move this down here to make more room. And then it's going to be plus 3t squared minus 18t plus 1, and that's all over h. And I'm going to distribute the 3. Negative 3t squared minus 6th minus 3h squared minus 18. Oh, that is plus, and I did that last time. Sorry. It is plus plus 18t plus 18h. Okay, sorry about that. I copied wrong. 18t plus 18h minus 1 plus 3t minus 18t plus 1 all over h. Okay, and some things cancel. Oh, and sorry, that was at squared. Okay, so negative 3t squared plus 3t squared. I have an 18t and a negative 18t. I have a negative 1 and a positive 1. And again, everything I have left has an h in it. So I'm going to factor out the h. And I have negative 6t minus 3h plus 18 all over h. And the h's cancel. So I can now do the limit as h approaches 0 of negative 6t minus 3h plus 18. And I can do this with direct substitution. So as h goes to 0, it would be negative 6t plus 18. That is my equation for instantaneous velocity at any given point on that quadratic. Okay, and that is the very last lesson, taking us up through 12.3.